Well, welcome to Chapter 17, the introduction to additional aspects of aqueous equilibrium. We're going to talk some more about acids and bases and how you can combine weak acids and weak bases to make what we call buffer systems. Buffer systems are very special systems, important in biology, important in all aspects of chemistry. What buffers do is they resist changes in pH, and we're going to learn how that works. So let me introduce you to stories of love and loss in Chemistry 1342. Maybe you know something about that already. We've all sort of lost, but maybe not. Maybe we've gained something. In any case, here we go. All right, so let's start out with acetic acid, which is a weak acid. And you know weak acids, they partially ionize in solution. Now, this is H+. I'm not sure you can see it, given that it's so lightly colored. This is H+, and this is acetate down here. And acetic acid, it only partially ionizes in solution. So the proton mostly stays at home. However, if this proton encounters hydroxide ion, and hydroxide ion we're just going to think of as big time base baby. And hydroxide ion, whenever hydroxide ion lays eyes on a hydrogen ion, there's going to be some chemistry that goes on. And it kind of looks like this. True love. And these guys are going to get together and they're going to make one of the most stable compounds around, water. Now, sodium cation isn't going to participate. It's going to buy a Harley and kind of tool around the country. So this is what I want you to take stock of. Anytime we take a strong base and it gets together with a proton from a weak acid, from a strong acid, it does not matter. The result is absolutely irresistible. They're going to make water together. Review, acid-base reaction. So the typical Bronsted-Lowry acid-base reaction involves the transfer of a proton. In this particular case, the proton will be transferred to the base, and they get together and they make the conjugate acid, and that leaves behind the conjugate base from the acid. So specific example here is HF, hydrofluoric acid. It's a weak acid. It's going to transfer this proton to hydroxide ion. Now this is actually going to be a big K reaction. A hydrofluoric acid normally has this small Ka, 10 to the minus 4, but if I throw some strong base into that solution, remember what the strong base does. It's going to grab a hold of a proton from wherever it can get it. It's going to leave behind the conjugate base, fluoride ion, and the conjugate weak acid, water. So weak acid with a strong base will have a large equilibrium constant. This is going to be a big K reaction. And what we say about big K reactions is they go all the way. Big K, all the way to products. So weak acid with a strong base will make a weak base. Okay, and here is your weak base and your neutral or negligible acid. And it's a conjugate. It's the conjugate of hydroxide, the conjugate acid of hydroxide. Strongly favored, big K, reaction if the reactants are stronger acid base than the products. So here we go. So this is hydrochloric acid. Hydrochloric acid is a strong acid. This is potassium hydroxide. It's a strong base. This is a big metathesis. Hydrogen and hydroxide are going to get together and make water, and potassium and chlorine, well, they're going to kind of hang out together, but they're not really going to make very much. So what you're going to have, if you combine a strong acid with a strong base, is a neutral conjugate acid and a neutral conjugate base. Neutral base, neutral acid. Here is a weak acid, this is acetic acid, and a strong base, barium hydroxide. They're going to swap partners. You're going to get barium acetate, and hydrogen and hydroxide are going to get together to make water. So what you'll get is a weak conjugate base and a neutral conjugate acid. Okay? Barium acetate will be the conjugate base of the weak acid acetic acid, and water will be the conjugate neutral acid from hydroxide. Okay, so you have a weak acid with a strong base, you get a neutral acid and a weak conjugate base. Don't worry about the barium ion. The barium ion is going to be a spectator in this reaction. It's not going to participate. Here is your weak base right here. It's the conjugate base of acetic acid. Here we've got ammonia. Ammonia is a weak base. This is perchloric acid. It's a strong acid. They're going to swap partners. The hydrogen ion is going to be gobbled up, or actually it's going to gobble up all the weak base, and then you're going to have the perchlorate ion hanging out as a conjugate neutral base. Okay, so you got a weak acid and a neutral base. Last but not least, you've got nitric acid. Nitric acid is a strong acid. Don't worry about the rubidium ion. It's going to be inert in this reaction. This is the bicarbonate ion. This is a weak base. And weak bases want protons in the Bronsted-Lowry sense. So it's going to pick up this proton, and then you're going to have some rubidium nitrate as your salt, which will be neutral. Okay, because you've got this is a strong acid, so nitrate is a neutral conjugate base when it shows up over here on the product side. So here we go. You've got a neutral base and a weak acid. This is carbonic acid. Okay, so here's a quiz. The quiz is for this acid-base reaction, and I'm just going to go ahead and show you how to do this. We don't worry about the sodium cation. Go back and review the section on salts. This is nitrite, and nitrite is the conjugate base of a weak acid, so it's a weak base. This is a strong acid. This reaction has a big K. It's going all the way. So the strong acid is going to force nitrite anion to accept this proton, and then you're going to get some sodium chloride as a neutral conjugate base. So your products are going to be HNO2, just the combination of hydrogen ion and nitrite ion. And then you're going to have NaCl. That'll be your salt. So A would be the answer. It's just a metathesis reaction, guys, and acid-base neutralization. What we wind up with over here is a weak conjugate acid and a neutral conjugate base. The neutral base is chloride ion, and we don't care about the sodium cation. It's a spectator in this reaction. Okay, acid-base reactions. When a strong acid or base reacts with a weak base or acid, the reaction proceeds to completion. Big K, anytime, guys, you have either a strong acid or a strong base, which we don't have in this particular case, it's a big K reaction, and that means it goes all the way to products. That makes it a limiting reactant reaction. Whichever one of these two reactants exists in the smallest amount will determine how many products we get. Okay? So this is a big K reaction. We've got a strong acid and we've got a neutral conjugate base. Here's a weak base and we have a weak conjugate acid. The conjugate acid-base pair together are weaker than the reactant acid-base pair. It's easy to calculate. So here we go. You need to get this. This will clean you up for the rest of the rest of this chapter. So this is going to be what we call ICF. Okay, we're saying that we have 0.10 moles of this. We're saying we have 0.05 moles of this. We don't have any of this to start. So this is a weak acid. This is a strong base. Because of this strong base in this reaction, it has a big K, and that means it goes all the way to products until something runs out. All the way to products until the limiting reactant is gone. In this case, the limiting reactant is the strong base sodium hydroxide. So that becomes our change. Minus 0.05, minus 0.05. We're not going to have any of this left at the end of this reaction. We're still going to have some HF. We'll also have 0.05 molar of this weak conjugate base. Remember, we don't care about the sodium cation, but we do care about that fluoride anion. It's the conjugate weak base to this weak acid, and we don't care about the water. The water is a neutral conjugate acid, and as a neutral acid, it doesn't have any impact on the pH. So we can ignore that. But over here, we're going to have 0.05 molar of this, and we'll have 0 plus 0.5 or 0.05 molar of the conjugate weak base. So here's what we have in solution. We have HF, and we have a 0.05 molar solution of it, or 0.05 moles of the stuff. We can decide how much volume we're going to have in a minute. We don't know how many H plus we've got. We've also got 0.05 moles of this stuff right here. Anytime I have a reasonably similar amount of weak acid in the same solution with its conjugate weak base, I have what we call a buffer system. And buffer systems resist changes in pH. They resist changes in pH. And how do they do that? By absorbing small additions. The addition of small amounts of acid or base. How would they do that? Well, the weak base can accept a proton, give us a little bit more weak acid. A weak acid can absorb hydroxide ion, make a little bit of water, and a little bit more fluoride ion. That's a buffer solution, guys. And that's what this whole section is going to be about. So once again, if I have 0.1 molar of HF, 0.05 moles of sodium hydroxide, this is a large K reaction. It goes all the way to products. The change is whatever is in smallest amount here on the reactant side, which is the sodium hydroxide. And so what that leaves us with is a little bit of weak acid, a little bit of conjugate weak base, and we've got a buffer solution. The common ion effect. Consider the weak acid, acetic acid, in equilibrium. Here's acetic acid in equilibrium with its ions. Now, if we just had, let's say, if we just had acetic acid, we threw it into water, it would partially ionize, and it would give us X amount of this and X amount of this. What happens if I take a solution of a weak acid like acetic acid, okay, so HC2H3O2, I throw it in a beaker full of water. It partially ionizes into its ions, H plus C2H3O2. But into this solution, I'm going to throw some amount of NaC2H3O2. Now, this is sodium acetate. Do we care about the sodium? No, it's a spectator. It doesn't do chemistry. So even though it's floating around and there's a free ion, I'm going to ignore it. But here's what I've just done by throwing the sodium acetate into this solution. I've jacked up the concentration of acetate. What does Le Chatelier's principle say when I add some product to this reaction? What's the shift going to be? The shift will be away from the addition of product toward reactant. And so that is going to change my concentration of weak acid. It shifts it back toward the reactant concentration. And when it does that, it lowers the concentration of hydrogen ion, because if it shifts in that direction, the hydrogen ion has to combine with the acetate to form the acetic acid. So that's what happens in that shift. So calculating the equilibrium concentrations when a common ion is involved. The next video does this problem for you, and we have a conversation about it.